So Babbage's machine, if he could have built it, would have been able to carry out any computation that modern computers can, although it would have needed a lot of space and a lot of steam. What else is capable of universal computation? Well, in complex systems, we kind of enjoy and love these little examples, these toy universes, cellular automata. So a cellular automaton is something typically a 1- or 2-dimensional grid, and at each grid location, we have a finite set of states. And one of our favorite examples, also a popular screensaver, is the game of life invented by John Conway. So in the game of life, each grid square can be alive or dead. Here the alive things are black and the dead things are white. And as in all cellular automata, there is a simple local rule where each grid point at each step looks at its own state and those of its neighbors, and then computes its new state, and everything gets updated in parallel. In this particular rule, the neighbors are the 8 locations in the grid that you could move to with a move of a chess king. And the rule goes like this. If you are alive and 2 or 3 of your 8 neighbors are alive, you stay alive. If fewer than 2 are alive, you die of loneliness. If 4 more are alive, you die of overpopulation, goes the story. This isn't really a biological model, but you know. Okay. And if you are dead, your square is empty, and you have exactly 3 neighbors that are alive, then on the next step, you will be alive. That's the whole rule. And Conway played with these numbers, these thresholds for being alive or dead, until it did something fun and interesting, basically. So one of the things that happens in the game of life is a little thing we call a glider. It's this little wiggly animal which travels across diagonally, and it'll keep traveling until it bumps into something. Then there's another thing called a glider gun, which shuffles back and forth and produces a stream of gliders. And moreover, it's possible to carefully design collisions between the gliders to build small objects or even to carry out logical operations. We can use the gliders, a stream of gliders, almost like a wire to carry a bit of information. Well, if you combine all these elements and you're extremely clever and you have an abundance of free time, you can build a Turing machine out of the game of life. So here we have a very complicated configuration in which the pixels are almost too small to see. I've zoomed in on one of the glider guns there, where across the diagonal here we have the Turing machine's tape, and here we have the head of the Turing machine. And so the game of life with a large enough initial configuration can simulate a Turing machine. There are some interesting questions here about, is it okay to start with a configuration which is infinite but periodic, that gives you all the tape you could ever possibly need? Or perhaps there's a clever way to have glider guns build the tape over time, starting with an initial configuration which is blank outside of a finite area. But anyway, the game of life can compute. It can compute because I just showed you how to build a computer in it. Remember a long time ago when we were talking about the NP completeness of certain problems, like the tiling problem, fitting in puzzle tiles into a certain shape, or the Hamiltonian path problem. And I emphasize that these problems are hard because you can build computers out of them. Well, here we're building universal computers, and given enough space and time in a cellular automaton, we can carry out any computation at all, not just one in, say, polynomial time or exponential time, the way we were talking about before. The game of life is a 2-dimensional cellular automaton in which it's fairly easy to set up a tape and a head which moves back and forth on that tape. So what about 1-dimensional cellular automata? Well, here is a particular 1-dimensional cellular automaton. Again, we just have 2 states, 0 and 1, or black and white, at each location. And again, we look at our nearest neighbors as well as our own state. And this is the update rule, where I'm showing you what the new state will be for the 8 possible neighborhoods, combinations of your own state and those of your neighbors. In fact, this is cellular automaton rule 110, because if these black squares are ones in the rule and the white squares are zeros, then in binary, this spells out 110. And Stephen Wolfram invented that numbering scheme as a way of exploring all cellular automata rules of a given size. So here is a space-time diagram of a typical run of Rule 110. At the top, we have the top row is some initial setting of all the cells in the grid, and time goes downward. And when you look at this, what immediately jumps out at you is there are all kinds of gliders. There are all sorts of different particles, if you will, analogous to the glider in the game of life, but with many types, which as we move down, they move left to right at various velocities. And you can see that when they bump into each other, complicated things happen. So it's tempting to think that we can build a Turing machine out of this. This was conjectured by Stephen Wolfram and then proved by Matthew Cook, and the two of them published this paper and showed that indeed Rule 110 is capable of universal computation, and therefore its long-term behavior, what will eventually happen from some initial state, is undecidable. And Turlock Neary and Damian Woods improved their simulation and showed that in fact it can simulate Turing machines with only polynomial overhead. In other words, it can simulate t steps of a Turing machine with an amount of time which is only polynomial in t. That means that predicting it, even for finite time, requires you to do a fair amount of work, about as much work as you would need to run a Turing machine for that amount of time.